Hi everyone, and welcome to Half Day Wednesday. So I'm going to review real quickly the nuclear physics we've covered so far, then give you one new vocab thing and send you to try today's quizzes. So far you and I have covered nuclear structure. We know that the nucleus is comprised of nucleons, that's neutrons and protons, and together they make the total number of nucleons in an atom. We can read this as 4 protons. That makes up the atomic number. And 7 nucleons total. So this nuclide must have 3 neutrons. On the outside would be its 4 electrons in its little orbitals randomly dispersed in there because 4 electrons match with 4 protons to make a neutral isotope. Now, depending on the stability of that nucleus, it could emit an alpha particle if there's just too many nucleons in the nucleus. A good example of this is radon. Radon is dangerous to humans because if we inhale it, then the radon decays to polonium plus this high mass, high charge alpha particle, which you could either write as an alpha or a 4,2 helium. And that particle is highly damaging and located in your sensitive lung tissue, along with polonium, which, if I recall correctly, does decay into lead, but in your lungs. Bad news bears. Okay, if there are too many neutrons, your cobalt-60 could transmutate by emitting a beta-negative particle. A beta-negative particle would have -1 as its atomic number. And you can either write this as E for an electron, because it really is just a high energy electron, or a beta symbol to indicate beta particle. But notice this doesn't change the total number of nucleons. There's still 60 protons plus neutrons in nickel. It's just one of those has changed to a proton from a neutron. Similarly, a magnesium-23 could turn into sodium, could transmutate into sodium by keeping its atomic number the same, but emitting a positron. I'm going to do the 10E symbol. You could also do the beta symbol. And these do emit neutrinos. It emits an antineutrino, 0, antineutrino with a beta minus, and a 0, regular, regular neutrino for a beta plus. But since those don't interact with matter very regularly, they generally get left off for our purposes. Finally, if your nucleus is an unstable configuration, it can emit a gamma particle, or how about we say this, a gamma ray, a high energy ray of light. So technetium-99, for instance, is an unstable isomer that will decay down to a stable state of technetium-99 by emitting a 0 gamma. All right, so then the stuff that was new since last Wednesday. Mr. Lubin went over half-life on Thursday. Half-life is the amount of time it takes for a sample to decay half of its mass away or half of its activity away. You could think of it either way. I did my graph as activity versus time. So imagine I have this Geiger counter over near my sample. And at 0 time, 100% of the sample is there. After 1 half-life, 50% would remain. After 2 half-lives, that would be 25. Right? So imagine my sample just keeps getting cut in half. So this would be at 3 half-lives, 12.5. At 4 half-lives, that would be 6.25. And this could go on and on forever technically, but functionally it would reach 0 eventually. Either your particle decays or it doesn't. So eventually, items with short half-lives can decay away completely. For example, technetium. All of technetium's isotopes are unstable with, relatively speaking, short half-lives. As a result, there's not much technetium left on the planet. It's a very, very, very low concentration because over time, all of it has decayed away into other elements. So there's very little technetium remaining on the planet. Whereas something with a long half-life, like uranium with a half-life of 4.5 billion years, persists in the ground because it has a long half-life. It just hasn't all decayed away yet. Now, we did mention that in math, we could use an exponential equation to solve these half-life problems. But I'm going to show you a different way that will help. Right? Now, please note, we're going to do exponential decay for half-life problems. Exponential decay as a function does look different than inverse square. Exponential decay has a y value, has a y-intercept, unlike inverse square, which we'll get to in a second. So, two super quick example problems. Iodine-131 has a half-life of 8 days. Now this is important because iodine-131 is very easily uptaken by humans and stored in the thyroid. You want to minimize exposure to this because then if you uptake this into your body, now this isotope in your thyroid is continually emitting radiation in your body. You are what's called contaminated. This is that new word I wanted you to write down. Contaminated means that you have taken in some sort of radioactive isotope into your body, and now you are emitting radiation from your body. This exposes both you and the people near you. If you are contaminated with radiation, I've heard other people write this as radioactive. You've taken those isotopes into your body, and as a result, you and the people around you are exposed to the radiation in that isotope that you've taken in. So this is super problematic with iodine because it gets stored in the thyroid, leading to thyroid cancers. This is the type that persists in the environment. And after Fukushima, in I want to say 2010, this was the primary concern. So let's say that on day 0, the Fukushima disaster occurs, which, to be fair, was earthquake followed by tsunami. Very hard to plan for. Earthquake followed by tsunami, it emits 100% of its radiation on day 0. And we want to know, after 64 days, how much is left persisting in the environment? Okay, so after 1 half-life, 50% is gone. After 2 half-lives, it's half again. After 3 half-lives, and actually let's just count this out, 8, 16, 24, 32, 40, oh my gosh, I made this too many days. 40, 48, 54, I'm mathing wrong, 56, 64. Right. Now that would just keep dividing in 2. So if 100% is on day 0, 50, 25, 12.5% remains after 24 days, 6.25 after 32 days, and we can see that this amount is getting smaller and smaller and smaller. So to save time here, for all of these half-lives to pass, right? So 1 half-life passed. That means your activity gets cut in half. So divide by 2. And we can repeat all the way down until we see how much is left. After 64 days, the threat from this iodine-131 has gone away. However, if you've uptaken the iodine into your thyroid, that means all of that radiation has contaminated you. You've taken in that iodine and it's emitted those beta particles directly into your thyroid. And then the beta particles that escape your thyroid and go out into the space around you can travel through air and hit people nearby. So, let's talk about another example. Fermium-255 was the first isotope discovered in nuclear fallout. It has a half-life of 20 hours. So let's say you have an initial size of sample at 60,000 particles. Okay? After one half-life, so after 20 hours, one half-life, there'd only be 30,000 of those left. They would have decayed into something else. After 40 hours, there would be 15,000. After 60 hours, there would be 15,000 divided by 2, so 7,500 particles. After 80 hours, divide that by 2, that would be 3,750. And after 100 hours, there would be 1,875 particles remaining. So, to compare these two methods, in example 1, we were trying to figure out how much activity remains. So what percentage of these particles are still decaying? A very small percentage is remaining decaying after 64 days. Whereas this problem, the second problem, was solving backwards to figure out how much time was passed. If we know that the passing of one half-life passed is equivalent to cutting the sample in half, both in size, that's number of particles, and activity, how many particles are coming out per second, right? Then we can use this backwards to solve for how much time has passed. Now, fermium-255 is a great example of something that irradiates people, but would not get taken into our body. So, as a contrast, a contaminated person becomes radioactive because they've taken that iodine isotope into their body. That exposes themselves and the people around them. But something like nuclear fallout, unless you breathe it in, let's hope you don't, this would cause you to become irradiated. You're going to get exposed to this radiation, but you're not taking it into your body. So when you walk away from this, I'm not saying you're safe. You've been exposed, but you're not contaminating others. Now, a good example of an irradiated or an exposed person would be that someone who gets a dental x-ray. You have been exposed to x-rays. You have been irradiated by them. It puts you at a slightly higher risk for genetic abnormalities. However, when you go home from the dentist's office, you're not like emitting the x-rays and endangering your family and people around you. So an irradiated or an exposed person is not emitting radiation on their own. In fact, a common use of radiation is to sterilize fruits and vegetables, expose it to large amounts of gamma radiation, but that doesn't mean your strawberries are emitting gamma rays at you. It's killed all the bacteria on the surface. The gamma rays have passed through the strawberries, but strawberries are not contaminated and they're totally safe to eat. Okay, which brings us to what we're working on now. The rest of the unit is dedicated to dosimetry and personal protection. And so far, you guys have done activity versus distance. If you are far from a radioactive source, imagine this is your source, those same 100 particles, we're going to imagine 100, now have to get broken up over not twice the area when you're twice as far away, but actually 4 times the area. Right? When you get twice as far away, that same amount of radiation has to go not twice as much area, but 4 times the area, meaning you get an inverse square relationship. If you start with 100 becquerels, that's 100 decays per second at 1 meter on your Geiger counter. Then if you take the Geiger counter and move it twice as far away, it would only read 1/4 of those. All right? Special things about this inverse square relationship here is that it very quickly decays. So at 3 meters, it would be 100 divided by 3 squared, 100 divided by 9, which is like 11 and change. not great at drawing, but forgive me. This is an inverse square relationship. And if you want to be able to tell them apart super easily, an exponential decay has a y-intercept. They both have asymptotes along the x-axis where they're heading towards 0 gradually. Okay? But exponential decay has a y-intercept. Inverse square law does not. If you go from 1 down to 0, you technically get infinite radiation over here. So the farther you are away, the less exposure you get. So, for today, go try the quizzes. Make sure to pay attention to the difference between contaminated/radioactive as opposed to irradiated or exposed. Okay, best of luck. Bye.